Hello, you're welcome. All right, so this is General Chemistry 1, and we are going to be looking at the key areas in this course. Okay, now very important key areas, and of course, these areas are the areas that you should be expecting in the semester examination. All right, so now let's start with significant figures because this course actually, of course, there are some topic in this course that you have to perform some calculations, right? And of course in that calculation you will definitely have to approximate. Okay, now, so what are significant figures? Now, significant figures are simply non-zero numbers. So when you are counting, when you have to count a significant figures from a digit, you have to start from a non-zero number. Now, for example, this is actually 0.0245628. So question is, how many significant figures do we have here? So I will not have to start from zero. No, I don't start from zero in counting a significant figure. I have to start counting from two. That's 1, 2, 3, 4, 5, 6, 6 SF, significant figure. So invariably understanding what significant figure is, you can actually you'll be asked to approximate. Okay, for example, you are using a calculator, and of course, after doing some calculation, you discover that you have a lot of digits. Okay, so now approximating that digit, and of course to be precise in your calculation, to actually have a good precision in your calculation, then there should be some number of significant figures to which you are going to approximate that value. Okay, so now let's look at some simple example here. All right, approximate to 2SF, two significant figures. All right, so solution, here we go. Two significant figures. Now for a part of this, okay, so this is 1 2. Okay, 1 2, the two significant figure have 1 2. That means this one here being the digit is the a significant figure, is the second significant figure. So I want to approximate at this point, at this digit 1. Okay, so what I would do, I would check the number after the digit to see if it is up to 5 or above. So if it is up to 5 or above, I will add it to this number. Then that is going to be the I have to neglect or ignore the preceding digits. Okay, so invariably this simply means that if I'm to approximate this, 2.10125 is approximately equal to, so this is approximately equal to 2.1. Every other digit after the approximation, all right, in as much as the digit is after decimal point, is significant, because I can actually replace them by 0000. So invariably this is 2.1. Now if this number after this the second significant figure is up to 5, I would have actually added 1 to the second significant figure, but since it's not up to 5, then I will do nothing about it. All right, so let's look at B part. So now I have 0.15, 0.1528. So, and to perform this approximation to two significant figures, so I'm starting to count from here. This is 1, this is 2, and of course the number after the please pardon me, after the second significant figure is not up to 5, so the approximation still remains 0.15. Okay, so that approximation still remains 0.15. But what if, let me add some, some numbers. What if you have something of this nature? Okay, so to approximate to two significant figure, of course this is 1 2. Now the number after the second significant figure is up to 5, so I'm going to add 1 to the second significant figure in my approximation. So the answer is going to be 3.2. That is to all of this approximation is to two significant figure, and of course, so please take note of that. All right, now let's look at how we perform calculation. Okay, how do we approximate when we are actually performing calculation? Now, majorly the calculation that we perform, all right, arithmetic calculation we perform in chemistry is basically multiplication and division. Okay, so now let's look at multiplication. Let's say you are doing some multiplication, right, and you have to approximate the value of your multiplication. For example, let's say I have this, you're multiplying this number. Okay, you're multiplying this number. Okay. Let me just put it this way. Okay, this is multiplication. So let me pick a calculator. So this is 1.25152, then multiply by 1.23. So look at the number I have, the digits. Okay, so the result I have is, if you can actually see that, is 1.53939696. Okay, so now the question is, how many significant figure am I going to approximate the result? Because the two numbers that is involved in the calculation are of different significant figure. This is of course two significant figures, while this right here is three significant figures. Okay, so invariably now the result of this multiplication I will approximate it to 1 2 3 4 5 6. Okay, the first number here is 6 significant figure, and of course this is 3. So I'm going to always approximate multiplication to the same number of significant figure, all right, of the number, all right, in that calculation that actually has the that have the highest significant figures. So invariably I'm going to approximate this to 6 significant figure. That's 1 2 3 4 5 6. Okay, so the 6 significant figure of this approximation, of course the digit is 6, and the number after it is more than 5. So that simply means that my result is going to be 1.53937. So the result of this is approximately equal to 1.5393, if I'm not mistaken, 5393, then 6, 53937. Okay, yeah, so that is the approximate value. So what the arithmetic is division? In the case of division, okay, so in the case of division, you are using the number with the lowest SF for the approximation. For example, let's say the division, we are dividing 1.2523 all over 1.52. Let's do this division. 1.2523 divided by 1.52. So look at what I'm having. All right, so now the number with the lowest significant figure here is the denominator, which is having 3 significant figure. So invariably, to approximate this, my answer is going to be 0.83. Of course, the 3 significant figure of this calculation is, of course, number 3 is 3. The digit is 3, and the number after it is 8, which is up to 5. So to approximate this is going to be approximately equal to 0.83 Okay, 0.82 then 4. That is how you approximate that. Okay, so that simply means that if you have, of course, some calculation actually involve the combination of multiplication and division. Okay, so it's possible for you to have something of this nature: 1.25 times 5.02 then divided by 1.82. So first of all, you work on the numerator, then approximate it, okay, using the same significant figure as the number with the highest significant figure. Then you now perform the division. All right, so please take note of that. All right, so please take note of this. Let's proceed now. Another thing that you should actually take note of is unit conversion, okay, in which we apply prefix to a unit either to convert it to a multiple. Okay, this prefix can actually be multiples of a unit. The prefix to a unit, okay, actually can represent the multiples to that unit, or it can actually represent some multiples. Okay, so let's take it one after the other. Now, multiples of a unit, the prefix that represent the multiples of a unit, okay, is such that if we are doing the conversion, we multiply by powers of 10. Okay, so now let's start with number 1. I have beta by capital letter P, which of course is 10 raised to the power 15, which simply means that anytime you want to convert any unit, okay, anytime any unit is given in beta, the conversion is always based on 10 raised to the power of 15. That is the multiples. Okay, so multiples we are multiplying, in sub multiples we divide. So invariably, let's say you are being given 2 petameter. So to convert to meter, all you just need to do is to multiply the 2 times 10 raised to the power 15 meters. Okay, so number 2. Now we have the tera, capital letter T. This is times 10 raised to the power 12. Okay, for example, okay, let me use a steel meter. Let's say you are being given 3 terameter. To convert that, you multiply the 3 times 10 raised to the power 15, of course, in meters. All right, then okay, so number 3, now we have the giga, capital letter G. This is 10 raised to the power of 9. For example, let's say you have to convert a 5 gigameter to meter. So that's you're going to multiply 5 times 10 raised to the power of 9 to convert that to meter. All right, let's proceed. Now from giga we have the mega, which is million. Once you hear the word, okay, of course this is that's million, okay, or mega, capital letter M. Of course, mega is 10 raised to the power 6, which is million. So example, 4 megameter is equal to 4 times 10 raised to the power of 6 meter. Then from mega we now have the kilo. Okay, this is 10 raised to the power of 3. Example, 1 kilometer is 1 times 10 raised to the power of 3, which of course is 1000 meter. 10 raised to the power 3 is 1000, right? So kilo is 1000. mega million, of course, giga 10 million. Okay, so of course that is it. So this is for the multiples. So anytime the units okay have this prefix, they are actually the multiples of the unit. Now let's look at the submultiples. Now the submultiples prefix, you convert it by dividing. Of course, that is it will involve reciprocal or negative power of 10. It will involve negative power of 10. So let me start from Pico. Okay, let me start from number 1, Pico. So now Pico, of course, this is small letter p. Small letter p simply means that you are converting it by dividing by 10 raised power of 12, or of course, or you are multiplying by 10 raised power minus 12. That's reciprocal. So reciprocal 10 raised power of minus 12. So invariably, for example, 2 Pico coulombs. Let me use coulombs. Okay, means 4 times 10 raised to the power of minus 12 coulombs. Number 2, okay, we have the micro. The symbol of micro is mu, and this is 10 raised to the power, okay, not the micro, before the micro, we have the nano before the micro, please pardon me. Nano by symbol n. Okay, so this is 10 raised to the power minus 9. 10 raised to the power of minus 9. Okay, so now 1 nanocoulomb. 1 nanocoulomb is equal to 1 times 10 raised to the power minus 9 coulombs. Okay, number 3, we have the micro. Let me list them out. Of course, 4. Okay, micro is 10 raised to the power minus 6. Okay, from the micro, we now have the milli. Small letter m. Milli will have the centi. C. Then we have the deci, which of course is deci is small letter d. Small letter d. Okay, so this is 10 raised to the power of minus 3. This is 10 raised to the power of minus 2. While this is 10 raised to the power of minus 1. So invariably, you're converting by dividing. Okay, so you can fill in the examples, any example that you want. All right, so I hope that is well understood. Now we are going to talk about composition of matter. Okay, so the composition of matter we are going to be discussing is element and of course the component of element. Of course, you know that every element is made up of atoms, so we are going straight to the point. Every element is made up of atoms, and atoms is said to be the smallest particle. Okay, smallest particle of an element. So invariably, anytime we want to represent the atoms of element, we use the symbol for the atom of that element. For example, this actually is the symbol for sodium atom. And now this symbol of sodium atom, there is a subscript attached to the symbol, and there's of course is a superscript. So this number here, okay, is once you see that number, that is the atomic mass of. So any atom, okay, that you have a number written up here, that number represents the atomic mass. And of course, I'm going to tell you what atomic mass of an atom is. Now, the number right here is the atomic number of that atom. So let's start with atomic number, which of course is the subscript. Now, the atomic number is by the symbol Z. Okay? The atomic number is simply by the symbol Z. Okay? It's the number of proton. The number of proton that is found in the nucleus of the atom. All right. Why the atomic mass of an atom, or even the it's either you call it atomic mass or you call it mass number, is the same, okay, or even the nuclear number. Now, the symbol of the atomic mass of an atom is A. What constitutes the atomic mass is the nucleus, is the particle that is found in the nucleus of the atom, which, of course, the particles found in the nucleus of the atom is the proton and, of course, the neutron. So, invariably, atomic mass of the atom is given as Z, which of course is the atomic number, the number of proton, then plus the number of neutron N. So this is how we calculate atomic mass of an atom. You add the number of proton, which is the atomic number, plus the number of neutron. So that simply means that the nucleus of an atom constitutes the mass of the atom. Inside the nucleus of the atom, you have the proton and the neutron. The proton is positively charged, the neutron is neutral. We are going to discuss more on that. Now, so as we said, this is actually, the nucleus actually constitutes the mass of the atom. So now let's look at how to measure the atomic mass of an atom. So we use this scale known as the atomic mass scale to measure the atomic mass of an atom. Now, why do we use atomic mass scale, and what is atomic mass scale? Now, you should know that atom, being the smallest particle of an element, is too small. So the mass of an atom is too small, of course, for calculation is too insignificant. You see something that is in, all right, in the range of 10 raised to the power minus 23. Very small, okay? So now, so for us to actually assign masses to atoms of an element, so masses that, of course, that is actually of a very good, a reasonable significant value, we have to actually assign mass based on comparison. So atomic mass scale is a way of, all right, a method of assigning mass to atom based on comparison. What do we use in our comparison? Okay, we use the stable isotope of carbon, that is known as carbon-12. So atomic mass scale is actually the mass that is assigned to the atoms of element, which actually compares the mass of that element with 1/12 of the mass of carbon-12. All right. What does this simply mean? What does it mean? So in atomic mass units, we have what is known as atomic mass scale. We have what is known as 1 atomic mass unit, 1 AMU. That's 1 AMU. 1 AMU is equal to 1/12 of the mass, 1/12 of the mass of carbon-12. So that is just one. So we simply mean that we use this for comparison. Okay, so this can actually help us to get the amount, the number of atomic mass unit of atoms of different elements. Okay, so let me actually illustrate this with an example. This is an example. Okay. Okay, let me take this off. All right, here we go. Okay, so all right, so this is an illustration. The average relative atomic mass. Okay. All right, here we go. Okay, so now the average relative mass of magnesium atoms is 4.0365 times 10 to the power minus 23 grams. Calculate its atomic mass if one atom of carbon 12 has the mass of 1.9627 times 10 to the power minus 23 grams and an atomic mass of 12 MNU. Okay, so now this is just very simple. I'm going to use the comparison that I showed you. So invariably, okay, so we know that one atomic mass unit, or AMU, because we are being asked to find the atomic mass, okay, of magnesium. So invariably, we are looking for the atomic mass unit of magnesium. But we know that one atomic mass unit is actually equal to, okay, so let me put this, one atomic mass unit is equal to 1 all over 12 of the mass of carbon. So already the question has given us the mass of carbon, which of course is 1.9927. So let's do that. So one atomic mass unit is equal to 1/12 of 1.9927, 1.9927, then times 10 raised to the power of minus 23. This is the value for one atomic mass unit. So we want to know the number of atomic mass unit that the magnesium, this mass of magnesium, okay? So what is the mass? So we want to know the number of atomic mass unit that this mass of magnesium will have. So that is where we apply proportion. So I can just call it X. I'll say that X atomic mass unit, all right, is equal to the mass of magnesium, which of course is given as, according to the question, 4.0365, then times 10 raised to the power of minus 3. So in this case now, for you to actually get the value of X, atomic mass unit of magnesium, this magnesium, okay, so magnesium, which of course is X, all we just need to do is to cross this. In this particular relationship, I will just, it's a proportion. This is proportion. I will just cross multiply. So cross multiplying, I have 1/12, 1 all over 12, or better still, S all over 12. Okay, S all over 12 of, if I'm cross multiplying, of 1.9927 times 10 raised to the power minus 23 is equal to, across multiply, 1 multiplied by this, that's going to be still going to be the same, 4.0365 times 10 raised to the power of minus 23. So at this point, I can still cross multiply again, or better still, to make S the subject, S is going to be equal to, if I cross multiply, I'm going to have 12 times 4.0365, then times 10 raised to the power of minus 23, okay, then divided by this, divided by 1.9927 times 10 raised to the power of minus 23. Of course, minus 23 cancels minus 23, so I have that S is going to be equal to, let's use calculator to do that. So 12 times 4.0600365, then divided by 1.9927. That is 24.3 approximately. Okay, 24.3 approximately. So X is 24.3 AMU, atomic mass unit. So that is why anytime the mass of sodium, atomic mass of sodium, anytime we want to use it in calculation, all right, we don't use this actual mass. This is the actual mass of sodium, okay? But we don't use this in calculation, but rather we use this mass of sodium, which we refer to as relative, okay? Relative atomic mass. And of course, the relative atomic mass is actually based on AMU, atomic mass unit. So all the mass of the atom, the relative atomic mass that you of the elements, okay, that you've ever used in calculation before, is actually gotten from the um, atomic mass scale. Okay, so please take note of that. So that is how we do that. So it's actually based on proportion. So comparing the 1 ammon, which of course is 1/12 of a mass of carbon, then to the mass that you want to convert. So I hope that is well understood. So please take note of this as we look at the next subtopic, which of course is isotopes. So what is isotope? All right, isotope. Okay, before you understand isotope, okay, now before you understand isotope, right, you should understand the phenomenon of isotopy. Isotopy is actually the existence of atoms of an element that with the same atomic number but different mass number. Remember, element is made up of atoms. An atom is the smallest particle of an element. Okay, so we simply mean that an element can be made up of thousands or even millions of atoms depending on the mass of the element. Okay, so now it is expected that all the atoms of an element should be identical. That means they should have the same atomic number and atomic mass. They should be identical. So that is why we should use just one symbol, okay, of one atom to represent that element. But we discover, okay, from the discovery, all right, of isotopy, it is of isotopes actually, okay, it has been proven that some elements exist as isotopes. Why? Because they have different atomic mass but the same atomic number. So for example, this is an element X which is having this symbol. Okay, so have the atomic mass A1, atomic number Z. Then in the same element, okay, this is one atom, and of course the same element is having an atomic mass of A2 but the same atomic number. All right, so of course this is just two isotopes. Now some element can have more than two, right? Some can have three. So now each of the isotope have the percentage to which they exist in that element. One can actually be greater in mass than the other. So that's the percentage to which they exist in that element. So it is that percentage of the different isotopes of the atoms of the element that will enable us to calculate the average relative atomic mass, all right, of that element. So with that, we can actually calculate the average relative atomic mass of the element. Now let's actually look at some typical example of an isotope. One typical example is the isotope of chlorine. Chlorine have two isotopes. One is chlorine 37 and of course chlorine 35. Now the percentage abundance, okay, or the percentage by mass of chlorine 37 is 25%. So chlorine 37 exists, okay, as 20 actually it's made up of 25% of the mass of the entire atoms of the chlorine element, while chlorine 35, okay, takes 75%. So it is the addition of this percentage abundance of these two isotopes that will give us the average relative atomic mass of chlorine. And of course, let's get it. So the average atomic mass of chlorine can be calculated from these two isotopes. So for chlorine 37, we have 25%, 25 all over 100 multiplied by the mass, which of course is 37, then plus chlorine chlorine 35, that's going to be 75 all over 100, then multiply by 35. So let's get the actual value. So using calculator, I have 25 times 37, of course, divided by 100. That gives that is given 9.25. Then plus, let's look at this one right here. 75 times 35. Okay, if you divide it by 100, that's going to be 26.25. 26.25. If you add these two together, you end up having 35.5. So that is why the atomic mass of chlorine, average atomic mass of chlorine is 35.5. So that is why chlorine is actually having a decimal value. So if you are being asked why are some the relative atomic mass of some element expressed in decimal point, is because those elements are, all right, they actually, that element have isotopes. They have isotopes. So please take note of that. All right, let's look at some example. Element T has two isotopes. So that is T35 and of course T37, two isotopes. Calculate the natural composition of this isotope if the atomic mass of the, okay, this is what just calculated, and this is chlorine. So the T represents chlorine. So we are looking at the percentage composition. All right, we are being given the atomic, we have been given the atomic mass of that, of the element to be 35.5. So look at how we calculate that. So from what we have, 35.5 is going to be equal to the percentage composition of the first element. Okay, let me call it x1 divided by 100, x1%. Okay, s1%, or let's just better still. So the percentage of composition of the first isotope is x1 divided by 100 by multiplied by the mass, which is 35. So then plus the percentage composition of the other is going to be 100. Remember, total percentage is 100. It's 100%. So if one is x, let me just use x. If one is x, that means the other is going to be 100 minus x. One is taking x, the other is 100 minus x. And of course, divided by 100. Okay, then multiply by 37. So all I just need to do is to simplify this. So this is going to be 35x all over 100. Okay, of course, multiply by, bracket open, this is 3,700, then minus 37x. Okay, that is, this is plus, please pardon me, this is plus actually, 35x plus, then the two fractions have common LCM, which of course is 100. The LCM is 100. So if I cross multiply, of course, open this bracket. Okay, so let's see what we are going to have. So if I cross multiply, I'm going to have this all over 1. So if I cross multiply, I'm going to have 35. I'm going to have 35x. Okay, bracket open, 3700. Okay, 3700, then of course minus 37x is equal to 100 multiplied by 35.5. That is going to be 3550. All right, so if I subtract this of course is going to be minus 2x. If I take this to the other side of the equation, that's of course going to be 3550 minus 3700. Let's subtract that. 3550 minus 3700. That is minus 150. So, okay, so minus 150. So invariably, x now is going to be equal to minus 150 that I got from this, then divided by minus 2. And if you do that, that's going to give 75%. So one of the isotope is 75%, while the other, okay, is going to be one is 75%, then definitely the other is 100 minus 75, which of course is 25%. So I hope that is well understood. Okay, so that is it for this video. In the next video, we are going to be looking at electronic configuration, or the arrangement of electron in an atom. So before we look at the arrangement, we are going to look at we are going to study atomic subparticles in details. All right, so see you in the next video. Thank you very much.